Welcome to Let's Learn Biomed. In this video, we will learn about the stability analysis of pupillary light reflex, which is a very important topic in physiological control systems. Pupil is a spherical and grayish aperture at the center of iris. It regulates the amount of light reaching the retina. The size of a pupil ranges from 3 to 4 mm. The size of the pupil is regulated by the parasympathetic and sympathetic muscles attached to it. It consists of smooth circular muscle called the sphincter pupillae and radial muscle called as the dilator pupillae. When sphincter pupil contract, the pupil decreases or constricts in size. The dilator pupillae dilates the pupil in contrast. The physiological function of pupil involves four pathways. They are pathway of light reflex, pathway of convergence reflex, pathway of accommodation reflex, and pathway of sympathetic discharge. Let us see in detail about the pathway of light reflex. The pupillary light reflex controls the diameter of the pupil in response to the intensity of light that falls on the retina. In human being, both the eyes constrict equally even when the light falls on any one of them. Greater intensity leads to constriction of the pupil and lower intensity dilates the pupil. This pupillary light reflex is of two types. They are direct pupillary reflex and indirect pupillary reflex. Direct pupillary reflex is a response to light that falls on same eye. An indirect pupillary light reflex is a response of the pupil when light enters the other eye. Numerous scientists have tried to develop a control system model which can replace the physiological working of pupillary light reflex. One such model was developed by Lawrence Stark and Alfred Linz to regulate the total light flux reaching the retina. An increase in the intensity of ambient light will elevate the total light flux received by retina, and the light signals will be converted into neural signals. The afferent neural information will be sent via the optic nerve to the lateral geniculate body and then to the pretectal nucleus. Subsequently, the Eden-Jervas nucleus sends efferent neural signals back towards the periphery to the iris sphincter and dilator muscle, which will lead to the contraction and relaxation of the pupil area. Starr came up with a linear characterization that provides a reasonably good approximation of the underlying dynamics when the changes involved are relatively small. A linearized model which can replace the physiological block diagram given in the previous slide was developed. He was able to functionally open the loop of this reflex and measure the dynamics of the system. He found that the dynamics could be modeled by a third-order transfer function with time constant r in series with a pure time delay d. In the above figure, del I represents a small change in light intensity from the reference intensity, while del A represents the corresponding change in pupil area from the reference value, and del L is the change in the total light flux reaching the retina. Based on the model explained in the previous slide, a closed-loop transfer function of the pupillary reflex was deduced. The loop transfer function of this model was given by HL of S is equal to k into e power minus Sd divided by 1 plus tau s the whole cube. Here, k is equal to Iref, the reference intensity, into k. Therefore, the characteristic equation for the closed-loop model is given as below. From his measurements on normal humans, Stark found the following values for the model parameters as k is equal to 0.16, D is equal to 0.18 seconds and R is equal to 0.1 second. The next two subsections, we will assume the above values of D and R in our analysis and determine the critical value of K above which the model becomes unstable. Now, let us apply Routh-Hurwitz's criterion method to understand the stability of the pupillary light reflex. The presence of time delay will complicate the physiological functioning of pupillary light reflex. Lardo and Son suggested that this problem could be circumvented by expanding e power minus st as a power series of s. Substituting the above approximation for e power minus st into equation and collecting the terms of each power of s, we could obtain a third order polynomial expression in terms of s. Now, we shall introduce the numerical values for D and R into this equation. So, the value of D will be 0.18 seconds and the value of R will be 0.1 second. From the equation that we have arrived at in terms of S, a Routh array can be constructed. The requirement for stability is that all the terms in the first column of the above array should have the same sign. Since the term corresponding to s power 0 is 1 plus k and k must be positive, then for the system to be stable, all terms in the first column of the Routh array must be positive. Thus, the following inequalities have to be satisfied simultaneously. Upon calculating the inequalities mentioned in the previous slide, from the first inequality, we can find that k should be less than 10.3. The second and fourth inequalities are satisfied for all values of k that are greater than 0. The third inequality, the quadratic expression in the numerator of the left-hand side, has to be factorized first. From this, it can be deducted that the inequality is satisfied if minus 24.196 is less than k and less than 1.996. Thus, combining this result with that from the first inequality, we conclude that for the closed loop system to be stable, k must be less than 1.996. Since the average value of k measured by Stark was 0.16, we can conclude from Routh-Hurwitz's analysis that the normal pupillary reflex is a highly stable negative feedback system. Thank you.